Hello everyone, welcome back. In this presentation, we will focus on prime factorization. In this presentation, I am gonna apply Fermat's factoring method. Let's dive into the outcomes first. Upon the completion of the session, the learner will be able to, outcome number 1, we will understand how to factor a given number using Fermat's factoring method. And outcome number 2, we will know about the pros and cons of this method. Let's dive into the topic of the day, the factoring method. As I already mentioned, we are going to focus on Fermat's algorithm. Why do we need this algorithm? Say you are given with a number n, and if you want to find the two prime factors of that number, then we need some technique to find it out. Say for example, you have taken two prime numbers 2 and 5. The product of these two prime numbers is 10. Say if you are given 10, you need to find out what are the two prime factors of 10, 2 and 5 in this example. So we want to find the values 2 and 5 given 10. That's what the topic of the day, Fermat's factoring method. So the main idea is to factor n, where n is the product of two prime numbers x and y. This can also be p into q. In this example, I've taken it as x and y. Say you are given with the number n, where that n is already a product of two prime numbers x and y, but you don't know what is the value of x and what is the value of y. You are given with the number n. And if you're required to find what are the two prime numbers that gave this number n, then we can go for this algorithm. But the drawback with this Fermat factoring method is that this algorithm works well when x and y are close. Say for example, you have prime numbers 5 and 7. 5 multiplied by 7, we get 35. If you are given with the number 35, you can use this Fermat's algorithm to find out the numbers 5 and 7, since 5 and 7 are close to each other. Anyway, this is a simple algorithm, so let me explain this now. So how we are going to do this? Please make a note of this formula, n is equal to x square minus y square. We know very well that we are going to find the two prime numbers of this number n, because this n is a product of these two prime numbers x and y. So I'm going to use the notation n is equal to x square minus y square. I'm not going to derive this how it has come, because this is not a mathematical lecture, rather this is a cryptography class, so I'm going to focus on the application areas. So I'm directly taking n is equal to x square minus y square. Say if you want to find the value of x, I'm just rewriting this equation as x square is equal to n plus y square. So this first equation is rewritten like this. Now as I mentioned, I'm going to find x. So x is equal to square root of n plus y square. Say we are going to use two formulas. One is this and the other one is this. So we are going to solve this problem by applying the value for y from 1, then 2, then 3 till we get a perfect integer this side. If a perfect integer is obtained for a certain value of y, then we are going to use this formula. I know things will be a little bit difficult at this stage. No worries. When we see an example, it will be clear for you. So before stepping into example number 1, please make a note of this formula. X is equal to square root of n plus y square for getting the perfect integer. Once we get a perfect integer, to generate the two prime numbers x and y, we are going to use this formula, which is equal to n is equal to x square minus y square. While waiting, let's dive into example number 1. The question is, factor n is equal to 187. So please note here, you are given with the number n. Now we are going to find the two prime numbers where the product of these two prime numbers is 187. So we are going to find those two prime numbers. Let's solve this now. What formula we are going to take? I already told you in the last slide that we are going to take x is equal to square root of n plus y square. We know the given data for n is 187. I'm just going to use this value 187 here. So we get x is equal to square root of 187 plus y square. As already mentioned, we are going to start with the y value 1. So let's start with y value 1. So we get x is equal to square root of 187 plus 1 square, which is equal to square root of 188. Square root of 188 is not an integer. So when we take the value of y as 1, we are not getting a perfect integer, because y equal to 1 has not produced an integer. Let's try with 2. So when we apply 2, we get x is equal to square root of 187 plus 2 square, which gives square root of 191. This is also not a perfect integer. Let's try 3. When we try 3, x is equal to square root of 187 plus 3 square, which is equal to square root of 196, which is equal to 14, which is a perfect integer. So we are going to stop at this stage. So we get x is equal to 14 and y is equal to 3. So we got two values, right? X is equal to 14 and y is equal to 3. Is this the final value? No, this is not the final result. Please note, this value of x and y are intermediate result. So this is not the final result. Yet we need to apply one more formula. Before that, let's see what values we got. X is equal to 14 and y is equal to 3. This is not the final result. Just recollect one more formula. What is that? N is equal to x square minus y square. How can we rewrite this x square minus y square? It is x plus y into x minus y, right? So we know what is the value of x here and what is the value of y here. So just place this this value in this equation, we get n is equal to 14 plus 3 into 14 minus 3. So 14 plus 3 is 17, 14 minus 3 is 11. These are the two prime numbers where the product of these two prime numbers is 187. So 187 is equal to 17 into 11, where the prime factors are 17 and 11. So the answer for this question, factor n is equal to 187, is 17 and 11. Let's see one more example. Let's see example number 2. Factor n is 17. And 11. Let's see one more example. Let's see example number 2. Factor n is equal to 3233. Let's solve this now. We know the formula is x is equal to square root of n plus y square. We will apply the value of n here in this equation. We get x is equal to square root of 3233 plus y square. So we will start applying with the value 1. When you apply the value 1 to y, you don't get an integer. When we apply the value 2, you won't get an integer. When you apply the value 3, still you won't get an integer. When you apply the value 4, you get square root of 3249, which is equal to 57. So from this, the value of x is 57 and the value of y is 4. This is not the final result. Please make a note of this. We have one more formula to substitute. Before that, let's write what is x and y. X is equal to 57 and y is equal to 4, which is this. So let's recall the formula. The formula is n is equal to x square minus y square. So this can be written as n is equal to x plus y into x minus y. We know what's the value of x and y now, right? So we will substitute the value of x and y in this equation. We get n is equal to 57 plus 4 into 57 minus 4, which gives 61 and 53. 3233 is the product of two prime numbers 61 and 53. So the answer for this question is 61 and 53. So before we sign out, let's see the homework question. The question is factor n is equal to 3009. I request you to solve this problem using this Fermat's factoring method and post your answers in the comment section. This algorithm works fine when the value of x and y are close. And that's it, guys. I hope now you understood how to factor a given number using Fermat's factoring method, and we know the pros and cons of this method. I hope this session is informative, and thank you for watching. In this presentation, we will see about testing for primality. What primality test we are going to see in this presentation? It's the Fermat's primality test. Let's see the outcomes first. Upon the completion of the session, the learner will be able to, outcome number 1, we will understand the Fermat's primality test with example, and outcome number 2, we will know the drawback of Fermat's primality test. Let's dive into the topic of the day, the Fermat's primality test. Firstly, we should understand what is this primality test. When you are given with a number and you are asked to determine whether the given number is a prime number or not. If it is a small number, you can easily work it out. Think if a number is given which is a big number. Then you need some technique to check whether the given number is a prime number or not. Primality test take number from the user and it determine whether the given number is a prime number or not. There are many primality tests. In this presentation, we're going to focus on the Fermat's primality test. So it's clear that we are going to determine whether the given number is prime or not. Say if a number p is given, is p prime? This Fermat's primality test is going to answer whether the given number is prime number or not. How it is going to determine whether it is a prime number or not? So obviously there is an algorithm, right? How that algorithm is going to work? It's based on the test. What test it is going to do? It's going to test a power p minus a. So when you are given with a number p to determine whether it is a prime number or not, then the algorithm is going to compute a power p minus a. What is this a? Let's see that now. P is prime if this is a multiple of p. It means p is prime if a power p minus a is a multiple of p for the values of a from 1 to less than p. A power p minus a is a multiple of p for all the values of a that are greater than 1 and less than p. So this primality test is mainly depending on the important formula a power p minus a. No worries, let's see an example, you will understand things clearly. Let's see some examples. Let's focus on the first example is 5 prime. I'm taking a small number so that you can easily understand the algorithm. Let's solve this now. From the question, it is clear that p is 5. We are going to determine, is this a prime number? So let's start from a is greater than 1 to less than p, which is 4. So we are going to do this operation a power p minus a for a equal to 1, a equal to 2, a equal to 3, and a equal to 4, because the value of a is greater than or equal to 1 and less than p. Since we have taken p is equal to 5 here, so a is going to take the value from 1 to 4. Let's start with a is equal to 1. For a is equal to 1 power 5 minus 1, which is equal to 1 minus 1, we get 0. Is 0 a multiple of 5? Yes, 0 is a multiple of 5. So 0, you can also write it as 5 into 0, right? So obviously 0 is a multiple of any number. 0 is a multiple of any number, so obviously 0 is a multiple of 5 as well. So for a is equal to 1, a power p minus a is giving the result which is a multiple of 5. Let's try for a is equal to 2. A power p minus a will give 2 power 5 minus 2. 2 power 5 is 32, minus 2 we get 30. Obviously 30 is a multiple of p, which is 5 in this case. Let's try with a is equal to 3. When a is equal to 3, we get 3 power 5 minus 3, which is equal to 243 minus 3, which is equal to 240, which is obviously a multiple of 5. And finally, we are left with only one value for a, which is 4, because the number we have taken is 5, and we are required to run this algorithm from a is equal to 1 to a is equal to 4. So already we have completed a is equal to 1, 2, 3, and we are left with a is equal to 4. Let's do that now. When a is equal to 4, we get 4 power 5 minus 4, which is equal to 1024 minus 4, which is equal to 1020. This is also obviously a multiple of 5. So we have calculated a power p minus a for a values from 1 to 4, where the result is obviously a multiple of 5, and the Fermat's primality test says this 5 is a prime number. I hope things are clear to you. But if you observe this algorithm keenly, there are few major drawbacks. One of the major drawbacks is if the prime number is a big prime number, then this process have to be carried out till that prime number minus 1. So that's the biggest drawback. We can evidence this drawback in the next example. Let's dive into example number 2. The question is 3753 prime? Let's solve it now. We know what we are going to compute. It's a power p minus a. And we are going to take the value for a as a is equal to 1, a is equal to 2, up to 3752. When we take a is equal to 1, we need to compute this for a equal to 2, for a equal to 3, for a equal to 4, up to we need to do this operation for a is equal to 3752. So this invites the biggest drawback that manually working out becomes a tough job. So it doesn't mean that you can't manually work out, but obviously it is a time consuming one and it takes a lots of effort to do it manually. Even if you ask a computer system to do this, think how many times that computer program needs to run this algorithm or run this loop. If this is p, then p minus 1 times the loop has to run, isn't it? Because that many times you need to verify whether the result of these operations is a multiple of this number or not, isn't it? So from this, it's clear that it is a time consuming one. And what about the accuracy? Can we 100% depend on the Fermat's primality test? For accuracy related things with respect to Fermat's primality test, I'm going to make you think. What I'm going to make you think? I'm going to give you a question. Is 561 a prime number? And I'm going to ask you to solve this question using Fermat's primality test. And obviously the answer is going to be either yes or no. That's what the Fermat's primality test is going to determine, whether the number given is a prime number or not. What is the answer for this question? Is 561 prime? Is it yes or no? And the actual answer is 561 is a composite number, which means 561 is not a prime number, but Fermat's primality test will say 561 is a prime number. As far as accuracy is concerned, we cannot 100% rely on Fermat's primality test. Though the algorithm is simple, it's a power p minus a, we are going to determine for all values of a from 1 to p minus 1. It's so easy and simple to implement, but there is always a lack of accuracy with Fermat's primality test. Anyway, please remember this number 561, and we will talk about this number elaborately in the next presentation. Before we sign out, let's see the homework question. The question for you is 11 a prime number? And you are required to determine whether 11 is a prime number or not using Fermat's primality test. Good guys, I hope now you understood. In the last presentation, we have understood the testing for primality. In that lecture, we have seen Fermat's primality test. In this presentation, we're going to focus on the Miller-Rabin primality test. As usual, let's start the session with the outcomes. Upon the completion of the session, the learner will be able to, outcome number 1, we will understand the Miller-Rabin primality test with example. Let's dive into the topic of the day, the Miller-Rabin primality test. We have two important personalities. He is the Israeli scientist Michael Ozer Rabin, and he is Professor Gary Lee Miller. Miller-Rabin primality test is the outcome of the hard work of these two eminent people. Let's dive into the topic of the day, the Miller-Rabin primality test. Miller-Rabin primality test, it is also called as Rabin-Miller primality test, and what this test is going to do, it's going to perform a probabilistic primality test. The result of the test will be whether the given number is a composite number or probably a prime number. This Miller-Rabin primality test is similar to the Fermat's primality test and the Solovay-Strassen primality test. This Miller-Rabin primality will be whether the given number is true. It's going to perform a probabilistic primality test. The result of the test will be whether the given number is a composite number or probably a prime number. This Miller-Rabin primality test is similar to the Fermat's primality test and the Solovay-Strassen primality test. In what terms they are similar? In the terms, this Miller-Rabin primality test is also going to check whether a specific property which is known to hold for prime values and holds for the number under testing. So a specific property is going to be tested, and based on that, it is going to decide whether the given number is probably prime or not. Let's see the algorithm now. I'm going to present this algorithm in 3 steps. Step number 1 is we are going to find n minus 1 is equal to 2 power k into m. Let's assume we are given with the number n and we are going to test whether that n is a prime number or not. So what we are going to do is in step number 1 we are going to find n minus 1 which is equal to 2 power k into m. After performing this, let's move to step number 2 where we are going to choose a number a. This number a is greater than 1 and less than n minus 1. Say if we are taking a number 11, then the value of a should be greater than 1 or less than 11. It means from 1 to 10 we can take any number. After choosing the value of a in step 2, we are moving forward to step 3 where we are going to compute b naught which is equal to a power m mod n. What is this m and what is this a? A we have chosen in step number 2 and m is the value we found out in step number 1. Using these two values, and we know what is n which is given in the question. So using these three values we are going to compute b naught and we are going to check the result of this variable b naught. If the result of b naught is plus 1, then it is a composite number. If the result of b naught is minus 1, then we can say it is probably prime. In case we are getting a value for b naught is neither plus 1 nor minus 1, then we are going to compute the next step b1. How we are going to do b1? b1 is equal to b naught square mod n. It means the next step b1 is the square of the previous step under mod n. If that result is also not plus 1 or minus 1, then proceed to b2 and then proceed to b3 till you get the value either plus 1 or minus 1. In general, I am writing it as bi is equal to bi minus 1 square mod n. So if you are going to perform b1, then this side is b1 minus 1, which is b naught, that is the previous step. So for b1, it is b naught square. For b2, it is b1 square. For b3, it is b2 square. And you are going to compute this till you get the result either plus 1 or minus 1. Don't worry about this now. When we see an example, you will easily understand. So let's dive into the example now. The question is 561 prime? Can you recollect this question? In the last presentation, I told you Fermat's algorithm passes this value 561 as a prime number. But actually, 561 is not a prime number. It is a composite number. Let's see what this algorithm says. Before going into step number 1, let's see what is the value of n. N is 561, which is given in the question. Alright, let's move on to step number 1. In step number 1, we are going to find n minus 1 is equal to 2 power k into m. N is given, which is 561. Then what is n minus 1? So 561 minus 1, which is 560. So I'm rewriting 560 as 2 to the power 4 into 35. So we can write 560 in powers of 2 as 2 power 4 multiplied by 35. So from this, we are finding two values. One is k and the other one is m. So what is the value of k here? It is 4. That is, this k is 4 and this m is 35. So we are getting k is equal to 4 and m is equal to 35. You may be asking me, is there any way to do this calculation easily? Yes, we can do this. Let me tell you how. Let's take the number 560 and we will divide by 2 first. So I'm going to carry out 560 by 2 power 1 first. Why? Because I need 560 in terms of 2, right? So 560 by 2 power 1, what value I'm getting? It's 280. So 560 by 2 power 1 is 280. Upon 2 power 2 is upon 2 power 3 is 70. So an integer. So I'm proceeding with 560 upon 2 power 5. So here I'm getting the value as 17.5. It means 560 divided by 2 power 5, which is 32. We get 17.5. So when we get a non-integer, what's the previous step? The previous step is 560 upon 2 power 4. So I'm going to take this. And this is how we can easily write 560 is equal to 2 power 4 into 35, which is this 2 power 4 into 35. See what approach I did? I have taken the number n minus 1. I've started with 2 power 1. If it is an integer, I'm going to the next step of dividing by 2 power 2. Then you need to follow this 2 power 3, 2 power 4, 2 power 5, 2 power 6 till you get a non-integer value. If you get a non-integer value, then the previous step you need to take. In this case, here we get a non-integer. So the previous step is 560 divided by 2 power 4 is 35. So 560 can be written as 2 power 4 into 35, which is this. We are done with step number 1. Let's move on to step number 2. In step number 2, we are going to choose the value of a. You can choose any value. Here I am choosing a is equal to 2. Is it satisfying the condition? A should be greater than 1 and less than n minus 1. What is n? 561. So n minus 1 is 560. So this condition is also getting satisfied. We are done with step number 1 and step number 2. Let's move on to step number 3. What we are going to do in step number 3? We are going to compute b naught first. What's the formula for computing b naught? B naught is equal to a power m mod n. So we are going to compute b naught equal to a power m mod n. What's the value of a? We have chosen in step number 2 a as 2. What's the value of m? We have calculated m to be 35 in step number 1. So we are just placing the values. A is equal to 2, m is equal to 35, and mod n is 561, which is mentioned in the question. Now after evaluating this, we get the result 263. So this is modular exponentiation. If you are directly watching this lecture, I request you to watch my previous lecture titled Modular Exponentiation to solve these kind of equations easily. So the value of b naught is 263. Is it either plus 1 or minus 1? No. Since b naught is neither plus 1 nor minus 1, we are going to proceed with b1. How to calculate b1? b1 is equal to the previous step b naught square mod n. What is b naught? That's what we calculated in this step, right? So we are going to calculate b1 is equal to b naught square mod n. Let's substitute the values. b1 is equal to 263 square mod 561. When we evaluate this, we get b1 is equal to 166. Is b1 either plus 1 or minus 1? No. So what we are going to do? We are going to compute b2. How to compute b2? b2 is equal to the previous step b1 square mod n. We will substitute the values, we will evaluate this, we will get 67 for b2. Again, b2 is neither plus 1 nor minus 1. Since b2 is neither plus 1 nor minus 1, we are going to compute b3. b3 equal to the previous step b2 square mod n. What's b2? It's 67. Let's compute 67 square mod 561. When you evaluate this, you get plus 1. Plus 1 means it's composite, right? So this algorithm says the number that we have taken 560. One is a composite number. 61 to be sign out. Let's see and solve this question and pay example. Hello everyone, welcome back. In this presentation, we will focus on group and abelian group. As usual, let's start the session with the outcomes. Upon the completion of the session, the learner will be able to, outcome number 1, we will understand the concept of group in number theory with examples. Outcome number 2, we will understand the concept of abelian group in number theory with examples. And outcome number 3, we will know various notations used for set of numbers in number theory. Let's dive into the topic of the day, the group. Firstly, let's see the definition. A group G denoted by G comma dot. It is a set under some operations dot if it satisfies the CAIN properties. Before I explain the CAIN properties, let me first tell you the group G is a set where it is going to contain a set of items. But this group is not referred as simply set. It is referred as group. Why it is referred as group? Because this set of elements under this operation dot, when it can satisfy these properties, then this set is called as a group. Now, what are the set of 4 properties, that is the CAIN properties, to be satisfied for the set to be a group under the operation dot? The properties are C for closure, A for associative, I for identity, and N for inverse. If these 4 properties are satisfied, then G comma dot is said to be a group. Please note here, this dot is a binary operation. It's going to take 2 inputs and going to generate the output. No worries, when we see an example, it will be easy for you. We are done with the definition of group. Let's now see the definition of abelian group. A group is said to be abelian if it is already a group and commutative property is also satisfied. A group is said to be abelian. Firstly, it should be a group. It means an abelian group should be satisfying these 4 properties: closure, associative, identity, and inverse. In addition to these properties, if the additional property, that is the commutative property, is also satisfied, then this group is said to be an abelian group. What is this commutative property? Say A dot B is equal to B dot A for all A comma B in G. When we see an example, then it will be clear for you. So before stepping into the example, let's see the properties. If it is a group, then it should be satisfying closure property, associative property, identity element should exist, and inverse element should also exist in the group. In addition to these properties, if the additional property, that is the commutative property, is also satisfied, then it forms an abelian group. Now let's see the explanation of each property. Let's first focus on the closure property. Let's take two elements A comma B that is belonging to the group G. If the A dot B operation we carry out and the result of this A dot B operation is also in the group, then closure property is satisfied. Then what is associative? A dot B dot C is equal to A dot B dot C for all the values of A comma B comma C that belongs to G. When this is satisfied, then associative property is also satisfied. Then what is identity element? Let's take an element A. When that element A is performed with the operation dot with the other element E, and when this A dot E or E dot A gives A again, then identity element exists in the group, where these A and E are also a part of the group. This is exactly identity element. And what's the next one? There exists an inverse element in the group. So if you take an element A, and this A should have its inverse in the group, so that this element A and its inverse under this dot operation will give the identity element which we have seen in the previous property, which is the identity property. So when A dot A dash, that is the inverse, when it gives the identity element for A comma A dash which belongs to G, then there exists an inverse element. When these four properties are satisfied, then it is a group. A group is said to be abelian if it is commutative. A dot B is equal to B dot A for all A comma B belongs to G. So we have seen the theoretical aspects of a group and abelian group. Let's see with an example. The question is Z comma plus a group? Let's solve it now. What is the Z? We know Z means it's a set of integers. So this is the set of integers, and this is actually a set. When we will call this set to be a group? When the four properties are satisfied, right? Let's see one by one now. Before stepping into that, the set of integers are all negative numbers, 0 and positive numbers are forming a set of integers which is represented as Z. Now let's solve this now. We need the CAIN property to be satisfied, right? Let me paste the properties now, which we have seen in the previous slide. Now let's deal with closure property. Let's take two elements A comma B from the group. See, we want to take the set of integers and we want to confirm whether it is a group or not. So what I'm going to do is, I'm going to take two elements A and B from the set which is belonging to this group. Then I'm going to perform A dot B operation. Here the operation that is mentioned is plus. It is the addition operation. So we are going to check whether the set of integers under addition operation is forming a group or not. Let's take any two elements. Let me take here A is equal to 5 and B is equal to minus 2, which belongs to Z, right? Now let's carry out the operation. What is the operation? A plus B. Because the operation dot here, it is mentioned as plus. 5 plus minus 2 will give minus 3, where minus 3 is also belonging to Z. Because this minus 3 is also existing in the group. So the first property is getting satisfied, which is called as the closure property. Let's now move on to the second property, the associative property. Let's take any numbers from the group. Let me take A is equal to 5, B is equal to 3, and C is equal to 7. 5 plus 3 plus 7 is equal to 5 plus 3 plus 7. Here we will have 15, here also we will have 15, where 15 is also belonging to this group, right? So obviously the second property, associative property, is also getting satisfied. Let's now move on to the third property. There exists an identity element. Say when you take the number A, you have an identity element in this group 0, so that any number under this operation, it will give the same number, right? So 5 plus 0 is 5, 10 plus 0 is 10, 100 plus 0 is 100. So you are getting the same number if you perform the operation plus, right? So there exists an element 0, which is also belonging to this group. So there exists an identity element in the group which is 0. So the third property is also getting satisfied. Let's now move on to the fourth property, the inverse element. Does there exist an inverse element? Yes, if you take a number 5, there exists minus 5. So that 5 plus minus 5 will give 0, which is the identity element, right? You take any number, say 20 belongs to Z, also minus 20 belongs to Z. So that 20 plus minus 20 is 0, where 0 is the identity element. So from this we confirm that there exists an inverse element in Z. So the fourth property is also getting satisfied. So it's clear that Z comma plus is a group because it satisfies the properties closure, associative, identity, and inverse, which we simply refer it as CAIN properties or Cain property. Already we have answered this question. Z comma plus is a group. Now let's check whether it is an abelian group. If Z comma plus to be an abelian group, then the fifth property, that is the commutative property, should be satisfied. Let's take any two numbers 5 and 9 which is belonging to Z. Now 5 plus 9 is equal to 9 plus 5 obviously. And the result, which is 14, which is also belonging to this set, right? So obviously the fifth property, commutative property, is also getting satisfied. We can say Z comma plus is an abelian group. The answer for this question is Z comma plus is a group, and also it is an abelian group. In this example, we have seen Z as one of the notations. Let's see what are all the various notations we have in number theory. See, we have many notations here. N means it's the set of natural numbers. W means it's the set of whole numbers. Z means set of integers. C means set of complex numbers. Q means set of rational numbers. R means set of real numbers. Z plus means it's the set of positive integers only. Z minus means it's the set of negative integers. Simply Z means it includes both positive and negative. Let's take one example. N, that is set of natural numbers, is set of natural number n comma plus a group. That is, we want to check n under the operation plus addition is a group or not. It is not a group. You know why? Because natural numbers does not include 0, where 0 is the identity element for the operation plus. Since there exists no 0 in the set, so obviously n comma plus is not a group. Likewise, you try finding answers for other notations. Before we sign out, let's see the homework question. The question is Z star comma plus a group? Is something weird here? Nothing is weird. I have simply mentioned z star or z star. It means there is no zero included in the set of integers. So you take z or z as set of all minus numbers, that is negative numbers, and set of all positive numbers excluding 0. So try finding the answer for this question and post your answers in the comment section. And that's it, guys. I hope now you understood the concept of group in number theory with examples. We also have understood the concept of abelian group in number theory with examples, and we also have seen various notations used for set of numbers in number theory. I hope you guys enjoyed this presentation, and thank you for watching. From the last few presentations, we have understood about groups and abelian group with examples. Now let's focus on cyclic group. As usual, let's start the session with the outcomes. Upon the completion of the session, the learner will be able to, outcome number 1, we will understand the cyclic groups with examples, and outcome number 2, we will understand about generators in cyclic group. Let's directly step into the topic of the day, cyclic group. Let's see the definition now. A group G, denoted by G comma dot, is said to be a cyclic group if it contains at least one generator element. When you have a group, obviously it should satisfy the 4 important properties: closure, associative, there should exist an identity element and an inverse element. When this G is said to be a cyclic group, G is said to be a cyclic group if it contains at least one generator element. No worries, when we see some examples, you will understand when a group is said to be a cyclic group and what is a generator element. Let's step into some examples. Question number 1. Prove that G comma star is a cyclic group where G is equal to 1 comma omega square. So we are required to prove G comma star is a cyclic group where this group contains 3 elements, 1, omega and omega square. Let's solve this now. In order to proceed with the solution, we should know the composition table. Let's see how to create this composition table. See what operation we are dealing with. It's star multiplication, right? So what we are going to do is we are going to create a composition table by having the operation as star here. Now what are the elements this contains? 1, omega and omega square. Let's fill these values in the row and column. So I'm filling the values in the row as well as in the column. Now just see, 1 into 1 is 1, 1 into omega is omega, 1 into omega square is omega square. So this is how we need to fill the table. Let me fill the table. Now I will explain you how it works. We know 1 into anything will be the same value, right? Similarly, 1 into anything will get the same value. So we are not bothered about this first row and the first column. Let's deal with only these 4 values. Let's start doing with this. Omega into omega is obviously omega square. And omega into omega square is 1 because we have values up to omega square. And what's the next value? It's 1, right? So omega into omega square is 1. Then omega square into omega is omega cube. In the previous step we saw omega into omega square is what? Omega cube, which is 1. Now omega square into omega is equal to omega cube, which is 1. And omega square into omega square is omega. How did we get this? Omega square into omega square is actually omega power 4. So omega power 4 can be written as omega cube into omega. We know what is omega cube. It is 1, right? So 1 into omega is omega. So this is how I completed filling this composition table. Why did I do this? What's the need for doing this? There is a strong reason behind this because we need to prove that this G is a cyclic group which is having these elements. And what is a cyclic group? A group is said to be a cyclic group if it contains at least one generator element. Here how many elements we have? 1, 2, 3 elements we have. So we need to prove that there is at least one generator element in the group. So obviously we are going to prove there are 3 elements in the group and we are required to prove that there is one generator element out of these 3 values. Now what is a generator element? Let's see that now. Since we have 3 values, I am making partitions for handling the calculation of all 3 values. Let's start with the first value 1. And what operation is that? It's star, right? So I'm going to proceed with 1 power 1. This is the first value I am taking. 1 power 1 is 1. What is 1 power 2? 1 power 2 is equal to 1 into 1, which is 1. 1 power 3 is equal to 1 into 1 into 1, which is 1. And 1 power 4 is obviously 1. So in this case, the element 1 generates only the element 1. How many times you apply this operation, you get only 1 as the result. Is it generating all the group elements? I mean, is this element 1 is generating all elements in the group like 1, omega and omega square? No, it's generating only 1. So this is not a generator element. An element in the group is said to be a generator element if it can generate all elements in the group. Here 1 is not generating all elements of the group. So 1 is not a generator element. Let's move on to the second element, which is omega. So omega power 1. You know why we are doing with powers? Because this is an operation star. We are going to deal with star operation. In case if it is plus, 1 square is equal to 1 plus 1. Please remember this point keenly. If it is plus, we need to proceed like if it is 1 cube, it is 1 plus 1 plus 1. This is how you need to carry out. So this operation is actually based on this operation. So let's continue dealing with the calculation. Omega power 1 is obviously omega. Just refer to this table. Omega power 1 means it's omega into 1, right? So omega into 1 is what? Omega. Now let's deal with the second value, omega square. We know what is omega square. It's omega power 1 into omega power 1. So just see the operation I'm carrying out is omega power 1, omega power 2, and then omega power 3. Omega power 3 is equal to omega square into omega. Just see omega square into omega. What's the value? It's 1, right? So we got 1. Let's try one more time. Omega power 4 can be written as omega square into omega square or simply omega cube into omega. What value we got for omega cube in the previous step? It is 1. So 1 into omega we get omega. Obviously, the element omega is generating all values of the group when it is being carried out with this operation. Just see what are all the elements of the group. 1 omega and omega square. We are able to generate 1 omega and omega square with this omega value or omega as the element. So we can say omega is a generator element. let's deal with the other element as well, which is omega square. So let's try with omega square power 1. Omega square power 1 means it's omega square into 1. So obviously it is omega square. You can refer this table. Omega square into 1 is omega square only. Then let's try with omega square power 2. Omega square power 2 can be written as omega power 4. This is omega cube into omega, which is obviously omega. Let's try with omega square power 3. Omega square power 3 can be written as omega power 6. Omega power 6 can be written as omega power 3 into omega power 3. You know what is omega power 3? Omega power 3 is 1. Omega power 3 means omega square into omega is also omega power 3 or omega cube, which is 1. So 1 into 1 is obviously 1. Let's try omega square power 4, which is omega power 8. We can write it as omega cube into omega cube into omega square. You know omega cube is 1. 1 into 1 into omega square, which is equal to omega square. Now we can also witness that the element omega square is also able to generate all the elements of the group omega square, omega and 1. So we are able to generate all elements of this group with the help of this element omega as well as omega square. So it's clear that 1 is not a generator element, omega is a generator element and omega square generator elements. Therefore, we can clearly say that G comma star is a cyclic group, and this is the answer for this question. Let's move on to question number 2. The question is, when does the group G with the operation star is said to be a cyclic group? So it's like similar to this previous question, whereas in the previous question we have given with the values 1 omega and omega square as the values in the group or the elements of the group. But here there are no values specified, so here they have simply asked when G with the operation star or multiplication is said to be a cyclic group. This is like a definition. Let's see the solution for this. Let's take one element that exists in this group G. Let's take this element X. Let's assume this X is belonging to this group G. And we are sure that G is already a group in order to be a cyclic group, right? Let's say we have group G. And G contains the set of elements out of which X is one of the elements in the group. So it's clear that X is one of the elements in the group. When X is in the group, then obviously there should be the inverse in the group, right? So the inverse for X is going to be X power minus 1 or 1 by X. Why? Because the operation is what? Multiplication. The identity element of multiplication is what? 1. When an element, when it is multiplied by its inverse, we should get the identity element 1, right? So obviously X inverse is the inverse element of X, which is also a part of the group, or which is also in the group. Also, we should have an identity element, right? So this 1 is the identity element of multiplication. So when you have an element X, when you perform with the operation star or multiplication, you will get X into X is X square, X into X into X is X cube, X into X into X into X is X power 4. So we will have all these values here. And these values will also have their corresponding inverses like x power minus 2, x power minus 3 and x power minus 4 and so on and so forth. This is the actual group that we are talking about. Now when we will call this group to be a cyclic group? When there exists a generator element, right? Let's say if this entire group is generated by this x, which is this. It means if this group contains x for some x, then we call G to be a cyclic group. This x is the generator element. So this is the answer for this question. Now in this example, we have talked about multiplication. Let's see one more example with addition. Let's see that now. Question number 3 is, when does the group with the operation plus is said to be a cyclic group? And we know we are going to take an element y, where this y is belonging to this group G. Let's take there is an element y. We know a cyclic group is basically a group. So obviously it will have an inverse element minus y. Why it is minus y? In the previous case it was y power minus 1. Because the operation is plus. Y plus minus y only will give the identity element 0. So minus y is the inverse that exists in the group, and 0 is the identity element that exists in the group. Also when you carry out this operation, y plus y is 2y, y plus y plus y is 3y, y plus y plus y plus y is equal to 4y, and so on and so forth. So obviously we'll get 2y, 3y, 4y and so on will be a part of the group, and also this group will be having its corresponding inverses, like y means it's minus y, 2y means it's minus 2y, and so on and so forth. So when does this group with operation plus is said to be a cyclic group? If there exists an element y and this y can generate all elements in the group. So the answer is, if G contains a generator element y, then we can call G is said to be a cyclic group, and this is the answer for this question. Here in this presentation I have given just the definitions and the explanation. In case if the question is given with the numbers as elements or some direct elements, you can apply the operation and you can prove whether it is a cyclic group or not. Please ensure that if the group contains at least one generator element, then that group is said to be a cyclic group. And that's it guys. I hope now you understood what is cyclic group with examples. Also we have understood about generators in cyclic group. I hope. In this presentation, we will focus on rings, field, we'll be able to, and the topic of the following properties: closure, associative, identity element should exist in that set, and there should also be an inverse element. If A1, A2, A3, A4, all these 4 properties are satisfied, then we will call it as a group. If a group is commutative, then it is an abelian group. So A5 should also be satisfied. We have already seen this elaborately in the previous lectures with examples. Let's dive into the first topic, rings. What is a ring actually? A ring R denoted by R, plus, star. If you notice here in the previous cases like in the group or in the abelian group, we had only one binary operation. But here we have 2 operations. One is addition and the other one is multiplication. Let's continue with the definition. A ring R denoted by R, plus, star is a set of elements with 2 binary operations called addition and multiplication, such that for all values A, B and C which belongs to R, the following axioms are obeyed. So what are all the axioms that should be obeyed if the set R, plus, star to be a ring? A ring must be a group first. So obviously it should satisfy properties from A1 to A4, and it should also be an abelian group. So obviously it should satisfy 5th axiom, commutative axiom. So a ring is obviously a group and also it is an abelian group. In addition to this, is there any other axioms to be satisfied? Yes, we have 3 more axioms to be satisfied. So all the additive related things are covered here. Let's focus on the multiplicative related axioms. It should be closure under multiplication. So I'm noting it as M1. So it's axiom M1. Closure condition under addition is already satisfied here under A1. Now we are talking about M1 where M1 is closure under multiplication. Let's take any two elements from R, A, B, which actually belongs to R. Obviously the multiplication of A and B is AB. This AB should also belong to R. So this condition should also be satisfied. In addition to this, it should be associative of multiplication. That is, M2 should also be satisfied. So A into B into C is equal to AB into C. If you note here, I am not mentioning the multiplication symbol. By default, multiplication symbol is applied. So for all the values of A, B, C, if it is belonging to R, then the result A into BC or AB into C must also belong to R. And also, this side should also be equal to this side. So if this is also satisfied, then M2 is also getting satisfied. And finally, we have one more condition to be satisfied. That is, it should be distributive. So this is axiom M3. Let's see the distributive laws, which is in the associativity, we have associativity of multiplication in M2 and we have associativity of addition in A2. We know associativity under addition or multiplication deals with the same symbol. But distributive means it uses both the symbols addition and multiplication. So A into B plus C is equal to AB plus AC. If you take A, B, C, all these A, B, C are belonging to R. It should also satisfy one more condition. It is A plus B into C, which is equal to AC, that is this, plus, which is this, BC. So as usual for all A, B, C belongs to R. So the distributive law should also be satisfied. Simply, if a ring R, which is denoted by R, plus, star, is said to be a ring if it is already a group, that means A1 to A4 is satisfied, it is already an abelian group, A5 is also satisfied, then M1, M2 and M3 are also satisfied. If all these conditions are satisfied, then the set what you are taking, that is R, plus, star, is said to be a ring. Simply, a ring will satisfy from A1 to A5 and from M1 to M3. That's it about rings. Let's dive into a commutative ring. Before that, let's have a note here. Please note the subtraction if you are going to perform A minus B is actually performed using addition only. Because this is actually performed with what? Addition only. There is no specific symbol for subtraction in rings. So what we are going to do here is A minus B can be done as A plus minus B. Both are same, right? So here, actually our intention is to do subtraction, but this subtraction is actually performed using addition, like A plus minus B. This is not a big deal because B is already there in the ring and minus B will also be there in the ring. Why? Because a ring is actually a group. So in that group, there will be an inverse element for B, which is minus B. So A minus B can be performed as A plus minus B. We are done with rings. Before diving into fields, let's see what is commutative ring. Let's see the definition now. A ring is said to be commutative if it satisfies the following additional condition. It should be commutative of multiplication, which is rule number M4. In an abelian group, we have seen commutativity of addition, and that is why we have mentioned it as A5. But here, a commutative ring means it is basically a ring. It means A1 to A5 and M1 to M3 conditions or axioms are satisfied. In addition to it, if it is commutative under multiplication, that is A into B is equal to B into A, for all AB that you take, it is actually belonging to R. If this additional condition is also satisfied, then the ring is said to be a commutative ring. Commutative ring means it has already satisfied A1 to A5, M1 to M3. In addition to this, it also satisfies M4. We are done with rings and commutative rings. Let's dive into integral domain. What is this integral domain? An integral domain is a commutative ring that obeys the following axiom. It means an integral domain is already in commutative ring. So obviously, A1 to A5 and M1 to M4 conditions are satisfied already. Now, in addition to this, M5 condition should also be satisfied, which means there exists a multiplicative identity. It means there is an element 1 which belongs to R. Why 1 belongs to R? Because it is a multiplicative identity. So we know the identity element of multiplication is obviously 1. If you have 1 that actually belongs to R, such that if you take any element A into 1 is equal to 1 into A. So the product of A and 1 or the product of 1 and A will give the same value A, where this A is actually belonging to R. So is that the only condition to be satisfied? No, we have one more condition M6 that should also be satisfied if it should be an integral domain. So there should be no zero divisors. It means if you take any element A, B that actually belongs to the ring and the product of A and B is 0, then either A is equal to 0 or B is equal to 0. If we are concerned about integral domain, please be noted that it already satisfies A1 to A5, M1 to M6, where M5 and M6 are exclusively for integral domain, M4 is for commutative ring, and M1 to M3 is for rings. Let's see about fields now. What is a field? A field F, sometimes denoted by F, plus, star, is a set of elements with two binary operations like the ring, which is called addition and multiplication. So in ring, we have seen it as R, plus, star. In field, we are using F, plus, star, such that A, B, C, any three elements that you take, it actually belongs to the field F if the following axioms are obeyed. What do you mean by this? It means this field is already a group and an abelian group, that is from A1 to A5 should be satisfied, and it should also be an integral domain. So obviously, an integral domain is a commutative ring, and a commutative ring is actually a ring. So from M1 to M6, all the previous conditions what we have seen should be satisfied. So in addition to this, M7 from E and in all fields, it actually infinity point M4 is if 6 that is commutative ring, and a commutative ring is actually a ring. So from M1 to M6, all the previous conditions what we have seen should be satisfied. So in addition to this, M7 axiom should be satisfied. It means there exists a multiplicative inverse for each A that belongs to F. Except 0, there is an element A inverse in F such that A into A inverse or A inverse into A should give the identity element 1. I hope things are clear to you because you're going to take an element A in F, which is the field here, so that for A except 0, for all other values in this field F, there should exist a multiplicative inverse A inverse such that A into A inverse or A inverse into A will give the identity element 1. We already know subtraction cannot be directly performed, right? We normally do subtraction using addition only. Likewise, if you are preferring division, this division can also be done using multiplication. How? Just see that now. See, A by B, if you want to perform, you can simply do it as A multiplied by B inverse. So you first need to find what is B inverse. So you have B, also you have B inverse belonging to this F, right? Because that's the basic requirement for a field. If you have an element B, obviously B inverse should exist in that field, isn't it? So A divided by B or A upon B can be done as A multiplied by B inverse. Let's see some familiar examples for fields. The examples for fields include the rational numbers, real numbers, and complex numbers. Before we see what is a finite field, let's consolidate whatever we have seen so far. If the set that you are taking is a group, then the axioms from A1 to A4 should be satisfied. If A5, that is commutative, is also satisfied of addition, then it is an abelian group. This abelian group is a ring only if M1, M2, M3 conditions are satisfied. This ring is a commutative ring, which is this, if M4, the commutativity of multiplication, is also satisfied. An integral domain is a commutative ring if additional axioms M5 and M6 are satisfied. A field is an integral domain if M7 is satisfied. Simply, group satisfies A1 to A4, abelian group satisfies from A1 to A5, ring satisfies from A1 to A5 and M1 to M3, commutative ring satisfies A1 to A5 and M1 to M4, integral domain satisfies A1 to A5 and from M1 to M6, and a ring satisfies the conditions from A1 to A5 and from M1 to M7. Before we sign out, let's see what is a finite field. A finite field or Galois field, which is actually named in honor of Galois, is a field that contains a finite number of elements. So a field with a finite number of elements is called as a finite field or Galois field. So what we are going to do with this? As with any field, a finite field is a set on which the operations of multiplication, addition, subtraction, and division are defined and satisfy certain basic rules what we have seen in the previous slides. If all these basic rules are satisfied, then it is a finite field only when it has a finite number of elements. The most common examples of finite field are given by the integers mod p, where p is obviously a prime number. Let's see the application areas of finite fields. It is actually applied in the areas of mathematics and computer science, which includes number theory, algebraic geometry, Galois theory, finite geometry, cryptography, and coding theory. And that's it, guys. I hope now you understood the concepts of rings, commutative rings, integral domains, fields, and finite fields. I hope you guys enjoyed this presentation, and thank you for watching.
I get the approach, but how to write the code for this question? It's a question of priority queue. How can I store the points? Actually, I can use where I can make an array of vector 2D vector and one map where I can store the points and actually match the points from the priority queue to get the actual answer. Make a for loop store all the square root of answers and match it with the points. Let's very close. To just go with I need to just go with whatever I'm thinking and find it whether it's right or wrong. First try, then confirm. Don't overthink firstly. I need to improve because this is the problem. Okay then, bye guys.